My name is Richard Ferrer, and I can say I am cloud hired.
That yes, come and join and get cloud hired. I'm cloud hired.
I'm cloud hired.
I'm cloud hired.
Hey, Go Cloud Architect family. I'm cloud hired.
Well, I'm cloud hired, guys.
So I'll just say I'm cloud hired.
I'm cloud hired.
I'm cloud hired thanks to Go Cloud Architects.
It worked for me, and now I'm cloud hired. Because of Google Architect program, I am cloud hired. See!
I am cloud hired. Thank you, Mike and the GlowCloud team.
Welcome, everyone. We are back for day 3 of our completely free Google Professional Cloud Architect Bootcamp to prepare you for the Google Professional Cloud Architect certification and exam. I am joined here by Leo Paredes. He's a member of our team, a very senior member of our team, and he and I will be your instructors throughout this program. In today's program, we will have about 2 hours of technical concepts and about a good strong 1-hour lab from Leo. And for the next few days, we're going to have some good, strong labs from Leo, which he can talk about in a little bit. But today, we're going to get involved in, obviously, our architectural components, but also a little bit of the tech and have a little bit of fun. If you've just joined us, and this is day 3 for some reason, and you just didn't know about it, day 1 or day 2, you can go back and see day 1 and day 2 on our YouTube channel. I'll have our team behind the scenes drop the links to those 2 things for you. I also want to let you know that we've got a completely free study guide, this 550-page study guide that the team made from my notes that I was going to use to teach this program. And again, you can sign up for it. It is completely free. It is in the chat box as well as the description of this video. And I want to let everybody know that tomorrow at 11 a.m., we're going to have our How to Become an Architect webinar. We have one every single week, but we're going to run this at 11 a.m., which is going to be earlier than normal. And we're going to do that because we've got this free boot camp in the afternoon. So I hope to see so many of you in the How to Become an Architect webinar. We'll talk about what we do as architects, what we really do versus what people think they do, because people think we do something different. They learn the wrong skills, and unfortunately, they don't have the skills, and I want you to get hired. We'll talk about what hiring managers want. We'll talk about how to get past HR when you don't have a perfect resume and still be able to get hired, and I will answer any questions you have. So come and join us. You want questions about, you want me to assess you, see if you're ready, you want me to check your LinkedIn profile, anything we can do on these free webinars, we will do for you. So, Leo, before we begin, you want to talk about what you're going to be demonstrating today around 4 o'clock or somewhere near that time when the time comes or so?
Sure, Mike. Today we will have some labs about VPCs, the virtual private cloud, the underlying infrastructure needed to create virtual machines and other services in the cloud.
Oh, networking things, my favorite and what I think is most fun, but I'm a network architect. So sounds great, Leo, when we look for that. Everybody, let me know that you are here. If you've just joined us, maybe invite a friend. Maybe let me know you're here with a hashtag Google Professional Cloud Architect in the chat box. Tell me where you're from. I'm over here in Port St. Lucie, and it is looking like it's going to be pretty bad storm-wise. So at some point, I have to find a way to get my cat in because she's outside running around chasing things. Leo, where are you today?
I'm in Sao Paulo, Brazil, Mike.
Well, sounds really nice right now. So Leo's in Sao Paulo, Brazil. Chris is over there in that Tampa, St. Petersburg area. But where are you? Let us know in the chat box as well. Awfully shy. No need to be shy. Architects, we talk to people all the time. It's like go meet people, build a relationship, ask them about their problems. So don't need to be shy. Adrian, you're in Phoenix. Actually, that's a nice place. I've been in there in the summer. Nice and hot and dry. I had almost no allergies there. It was kind of great. Adam in Los Angeles. I've spent some time there. I just got back from there, actually. I mean, technically, I was in Beverly Hills, but I was staying for most of what I had to do. And then I stayed in Santa Monica, which I've always loved. Daryl's in Chicago. Tish is in Atlanta. Love that. Actually, I love Atlanta. My wife and I are always going there. Either we're in Atlanta, we're in Peachtree City, we're in any of the places around the Atlanta. We always go to Alpharetta. And Darnell in Chicago. All right, let's begin. Okay, now we get to some of the fun part, the networking. And the next section of preparation for the Google Professional Cloud Architect exam is networking. Now, I can't go into a huge networking course during this program, but networking is going to be very critical. So I'm going to give you a couple options. On our YouTube channel, we have a free CCNA boot camp, which will give you a lot of information on networking. We have subnetting workshops. We have BGP workshops. And please do check them out. There's a set of networking labs that you can watch through, but we walk you through so you'll really learn networking a lot more than we could ever cover in one of these exams. So please go check that out. I think it'll help you so much. So networking is the ability for the systems to actually talk to each other. And without a network, we have absolutely zero. If I had one computer here sitting in one room and there was no network and another computer next to it, the two couldn't talk to each other. So keep that in the back of your mind. For everything to work, we need a network, and the network needs to be well planned and fully operational. So in the cloud, the network's going to connect our resources together. You're going to need a network to connect to the cloud, and that's typically where we're going to be dealing with a lot of networking concepts. Now, these will still be basic networking concepts, but we're going to get involved in a lot of networking concepts. So let's have fun. The first thing I want to talk about is your three kinds of networks you'll typically work with. And we're going to draw them out as LAN networks, which are local area networks, metropolitan area networks, and then wide area networks. And then I'm going to draw it out architecturally the way we would typically connect to our cloud providers so you could see this and understand before we begin the networking discussion. So we have first this concept of a local area network. And a local area network is what you have in a local area. So typically speaking, inside of a building. Now, we could have two buildings next to each other, and we can have a piece of fiber optic cable under the ground, and that's still considered a local area network. But a local area network is going to be where your things are typically. So I'll give you the example here is here we've got the building. And the building's going to have a bunch of routers. And then the building's going to have some switches. So let's just say we have routers and inside of the building. And then we have switches inside of the building. And our servers plug into the switch. For example. And we could have users on another set of switches. And that we can have some users here. And what will happen is the users will be able to access the systems because they're plugged into the switch, which is plugged into the routers. The routers are connected to the switches. So a user here on the local area network wants to access something on a server, and they do. Now, you won't know it, and they won't really talk about it, but you want to know exactly how the cloud providers operate? They have their buildings called their data centers, and inside of their data centers, they've got a whole lot of routers and switches, and they've got their servers and their storage plugged into these switches, and that's how everything works. Now, that is what we called a local area network. Now, the next thing we have is something called a metropolitan area network. No, most people refer to the local area network as a LAN, and typically speaking, you hear a metropolitan area network often called a MAN. I didn't make up these terms. And realistically speaking, what is your typical metropolitan area network? So let's say you've got a building, and then you've got another building that's, say, 30 miles away. And then you've got another building that's, say, another 30 miles away. And what you do is you get these underground fiber optic cables between your organizations. And this is called the metropolitan area network because basically it's over a city. Now we're going to talk about a wide area network. And here's a wide area network. We've got a New York office. We have a London office. We have a router on both sides. Oops, didn't mean to do that. And we bought a 10 gig Ethernet link, private line in between these environments. This is called a wide area network. But you know what also is? I'm going to show you. And the reason I drew this out is so you would get it for cloud computing. So let's say this is the customer. And they want to access their system securely, which most likely they will be, meaning not over the internet, over their private environment. And their critical systems, they're not going to want to be reachable over the internet. So let's say you've got your systems and over here, and it's the cloud provider. In this case, it's the Google Cloud because we're doing the Google Professional Cloud Architect certification. Now, in most cases, it'll be multiple cloud providers. But here you do. You've got a connection on both sides. And you need a wide area network that you could use to the cloud provider. Now, you could create a VPN tunnel through the internet. You could get a private line between these two. And if it matters, you're going to use a private line. And all of a sudden, now you're here connected to the cloud provider, and you've got a local area network in your customer site where all your users are plugged into that are in the environment. And look at this, and I want you to see this. So I'm going to put user. Now, because we have a wire between us, or the equivalent of a wire, all the users in this LAN are not traversing the internet, which is a terrifyingly scary place to get their information from the cloud provider. If you wanted to manage the systems, you didn't need a Bastion host. You could do it directly from the local area network and the wide area network connecting the two. So this is your network that you could have. Now, there's options we could use here, like a private line, IPsec VPN, a software-defined WAN, a SASE WAN. Obviously, that's a lot of architectural training that's way, way, way beyond the scope of this. It's in our architecture courses. And there's also some video discussions of these types of wide area network technologies that you can see on our YouTube channel. But if it need to get deep, it's inside of our architecture program. So those are the three kinds of networks that you typically need. Now, how do we determine which one of those we need? It'll be based upon the kind of access we need. And realistically speaking, we would use a private line if we need guaranteed bandwidth. We would use a VPN if we don't need any guarantees and we want to use our internet connections. And often a VPN is much faster to set up and it's often potentially cheaper. We'll get to these wide area network connections later, but I didn't want to start a discussion on networking without actually getting there. Which brings us to the virtual private cloud. Remember, the virtual private cloud I showed you on the first day is your virtual private data center. It is a private network that you've carved out, or the cloud provider has carved out just for you inside of their systems, logically created. This is where you're going to put, because it's your virtual private data center, this is where you're going to have all your network stuff. And because of your network, all the other stuff will be logically plugged into your network. So this is where you'll put your IP address ranges, like your CIDR range or subnets. You may have access lists, your firewalls, load balancers, all that stuff. All the same networking that you would ever have in a data center is going to be identical same networking on the cloud. Other than in the data center, it's going to typically perform faster and it's going to be hardware based. And in the cloud, it's all software emulated versions of the same networking thing. So keep that in the back of your mind. Now, Google has a global network. Obviously, they've got data centers all over the world, and they also have global networks. So you can create your virtual private cloud across multiple regions and give yourself a single network of resources. Or you might want to separate it out for security purposes to not all be in a single virtual private cloud. Limit blast radius, what have you, segment your system, but you do have the ability to do that. Now, when it comes to putting IP addresses, you're going to be like any other network. You'll have your CIDR range, and maybe I'll map this out for you to kind of explain this the way it would be done in networking. So typically speaking, you'll have your CIDR range, and I'll give you an example of what that would be. So if we had the 172.16.0.0/16 CIDR range, what does that really mean? It means this contains every IP. Well, let me change that to 172. So we stay with private addresses. It means that every IP address from 172.16.0.1 all the way to 172.16.0.0.255, which would, of course, be the broadcast address, is all contained inside of this. Now, here's something to know about networking, and you'll see why we have to subnet it. And again, we've got a multi-hour subnetting course completely free on our YouTube channel, so please do check that out. But what we would typically do is we would then further take this down to something smaller. So we might use for a LAN segment a /24. So for example, if all we needed was LAN segments, we could basically create 172.16.0.0/24. And /24 is typically a good size for a LAN segment because it gives you upwards of 253 hosts you can put on a segment. And even if you think you only need like 50 servers on a segment, you may add capacity, you may want auto scaling. So a lot of us network architects use what's called a /30 on a WAN traditionally, because there's only 2 IP usable addresses on that subnet. And realistically speaking, we didn't waste as many addresses. And I'll show you next why we have to subnet. But what we could do is we could use this as a single subnet on one link. And then the next LAN subnet, we could use a .2. And then the next one, we could use a .3 if we wanted. Now, the planning of this out takes time. It's typically a CCIE level or better skilled in how to plan these IP addresses. And if the IP address plans are done wrong, the architecture will fall apart. It's like, because the IP addressing affects the routing. And it's like, imagine planning a street, planning a city, and not thinking about how many people would be on the streets and if they would even drive on the streets. So we can see cities that are old, which can't really accommodate cars very well because no one planned on cars being there. Same thing for IP addressing. So we would further subnet these down. Now, why do we have to subnet things? We have to subnet things for this reason. Every interface on a router or a switch has to be on a different subnet. So I want you to understand this. So this means that if this is a router and the router has four ports on it, and each port is obviously on a different subnet unless it's a switch router. So let me just draw 4 LAN segments on here, and I'll show you what I mean of why we have to be very diligent with IP addresses. Bear with me. I'm going to draw another. Each one of these is what you would, with the standard graphic, if you will, for a LAN segment. So let's just say we didn't use subnetting, and I want you to see what has to happen. So every subnet has to be, every interface has to be in a different subnet. So imagine for right now, and these are public addresses, we're not going to use them. This is just for an example purpose. Imagine if, let's not even do that. Let's imagine we put 10.0.0.0/8 on this link. Now, the 10.0.0.0/8 actually has approximately 16 million usable IP addresses in it. But if we put that on this interface, we couldn't use any of those addresses ever again. So that might mean we would need to use, let's say, this is now we're getting into a public address, so we're just going to ignore it. Let's just say this was 11. And let's say this subnet was a 12. and /8, and then let's say this one was a 13/8. Now, we basically used 16 million plus IP addresses on this link, another 16 million on this link, another 16 million on this link, and another 16 million on this link, which means we just burned through 64 million usable IP addresses that we could have used like that. So by comparison, if these were WAN links, not LAN links, but what we typically use is a /30. So imagine this, 172.16.0.0/30, and that would give us in that case we'd have the usable addresses of .1 and .2. You can check out our subnetting video to learn why. Now imagine that this next one, for argument's sake, we used was .4. So far we've used a total of 4 IP addresses here, another 4 IP addresses here of usable addresses. Now in the next, let's assume we used another /30 on this segment over here. Let's bear with me. And then you could see how, let's make this a .8. And then of course we need one more subnet to make this work. That's going to be the .12 subnet. So after we subnetted this down, instead of wasting 64 million addresses like we previously did by using the CIDR range, ultimately what we did is we burned 16 addresses and we needed 8 of them, which isn't very wasteful, versus previously we burned over 16 million and we only needed to use 8. That's why we subnet. And when it comes to anything on a network, it's going to need an IP address. If I sent you mail to your house and you lived in 123 Main Street, let's say Main City, Georgia, I just made it went up at postal code 123456778, and again I made that up intentionally so we didn't use anything real from someone, but that identifies you. That's how the mail delivery service knows how to find you, or the postal service, wherever you live. Every IP address needs a unique address. Internally, we use private IP addresses. And you can learn more about the private IP address space if you want to read the Internet Engineering Task Force, RFC 1918. And it specifies the private IP address space, which is the 10.0.0/8, the 172.16.0.0/12, and the 192.168.0.0/16. Those are the private address spaces that are out there. And you'll use that internally. Now, anything that is going to be external and needs to be reachable by the internet will need a public IP address, or at least the load balancer in front of it will need a public address, or something to that effect. Now, Google can let you use an automatically dynamically signed IP address, or you might want to statically configure it so you know exactly what the address is going to be, because you might need to configure certain things in your firewalls and other things along the way. So you've got both options. Now, we can create firewall rules, which will basically block network traffic like a packet filter. And users can assign firewall rules to allow certain things. What do I typically mean by this? I will show you. We can say, let's say we have a server, and it's an internal server. Let's say the only subnet that should ever be able to reach this server, that should ever be able to access it, is 192.168.2.0/24. And this particular subnet is where the developers and systems administrators and everybody that needs to access that subnet actually sit. So what we can do is we can create the equivalent on all networks of an ACL, an access control list, which is going to be a non-state listing, or an actual stateful firewall, or even a next generation firewall, or any kind of firewall we need. We can say on this one, permit 192.168.2.0/24, so we know it gets the entire subnet, to be able to access port 443 on the server. and then we would put the server. And then what we would do is everything else would be blocked. So one of these users tries to access this server, and they're allowed. Now, all of us, the next thing you know, we get a user, and this next user is coming from this IP address. And as soon as that packet hits this firewall here, it's just dropped. Now, we'll have the ability, typically speaking, in cloud computing to protect subnets, to be able to protect specific devices. There are a lot of firewall rules and types of firewall things we can apply on the cloud provider. But I wanted you to understand. So I thought a basic visual would possibly be helpful. So I hope it was. Now, on the cloud, we're also going to be needing load balancing. And load balancing is not new to the cloud. Load balancing is something that's been around forever and ever, which we've used in the data center, and we'll talk about what that is. Load balancing enables you to distribute traffic to more than one device. Now, why might we use this? Well, load balancers themselves improve performance, and they also improve availability. And we use load balancers to distribute traffic. Let me give you an example. I'll whiteboard some with you so you understand. Imagine an environment right now where we have one big server, one super powerful server. And this is a super powerful server. And right now we're operating at 3% capacity. And this server can go and has 97% more capability. Well, we don't want it to go that high, but let's just say this server's got, we never wanted to go above 90%, or actually we don't want it to go over 80%. So let's say we have 77% additional capacity left in the server. Well, what happens if the server crashes and goes away? What happens if the server's dead? Well, guess what? Our application is dead. The users of the application is dead, and our systems are down. So this may not be the most optimal situation. What might be more optimal, for example, is we have this load balancer. And in the cloud, the load balancers are high availability devices that don't go down. In our data center, we would use 2 data centers. But now let's say we have a large number of smaller servers, for example. Now what happens here is now we have 4 servers instead of just single. Now this is a logical device, and in the cloud it could be distributed across 100 different servers, so they don't typically go down, so you don't worry about this being a single point of failure in the cloud. In a data center we use redundant load balancers because they're real devices. But now if one of these servers goes away, the rest of the load balancers take over the load. So how is this going to work? And this is going to work in DNS, very similar ways. It's going to work with our load balancers. So what's going to happen is the load balancers themselves are going to do some flavor of a health check. Server 1, are you there? Yes, I'm here. Everything's good. Server 2, are you there? Server 2 says, yes, I'm here. Server 3, are you there? Yes, I'm here. Everything's happy. Server 4, are you there? Everything's happy. I'm doing good. Now, this continues to occur. So let's say server 1, are you there? I'm here. Server 2, are you there? It doesn't respond. So it checks on server 3. Are you there? Server 3 is there. Server 4, are you there? Yes, I'm here. Now, again, the load balancer checks server 1. Yes, I'm here. Server 2 does not respond to the health check. What's going on with server 2? Server 3, are you there? Yes, I'm here. Server 4, are you here? Yeah, I'm here. Server 1, are you there? Yes, I'm here. Server 2, no response. Okay, not load balancers now says, this server is dead. Don't send any more traffic to it. So the load balancer marks it as something, and every load balancer has its own way that it does it. But basically it says, this server's persona non grata, don't send anything to it. And now the load balancer sends to the other servers. Now, potentially speaking, you could have auto scaling and add an additional server because one server's even down. And that case, it can further self-heal your environment, but that's what the load balancer is doing. Now, we're going to have 2 kinds of load balancers that we can typically deal with in all cloud environments. And we're going to have network load balancers, and we're going to have something called application load balancers. And they are similar in function, but they're slightly different, and I'll explain the difference. A network load balancer is not a highly intelligent device. So when a packet comes into the load balancer the load balancer looks, it's TCP with the protocol TCP, ID, like UDP, ICMP, the source address, the destination address, and poof, it sends it to the servers. It's not looking at that much. It's looking at certain things, layer 4 type information. And because of that, these load balancers are fast. They send traffic at an alarming, blazingly fast rate. So imagine if your servers have 384 cores. You're going to want a network load balancer to deal with these blazingly fast servers. Now imagine if this wasn't a server, but this was a firewall or a route that you were load balancing amongst 4 firewalls, because no one firewall was strong enough for you and you needed high availability. Now, again, you're still going to use a network load balancer because networking things have to be fast. So we use network load balancers when we need speed. Now, it's not looking a lot. It's looking into the headers, the layer 4 stuff, source, destination, protocol, port, that kind of stuff. So because it is fast, and I ask you, how fast can you do 2 plus 2? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Pretty easy, right? It's not complicated. Now, the application load balancer looks into much more. It looks deep into the packet headers. It could look at the HTTP or HTTPS method routing, push, get, what have you. It can dive deep. And because of that, application load balancers are highly intelligent, but they're fairly slow. And they're slow because they're doing a lot of work. So if the network load balancer was 2 plus 2, which we did was pretty quickly, what if this was calculus? You can see you can't get out calculus problems as fast as you can. So where might you use the application load balancers? Small servers, little mini servers that you might have. You might use an application load balancer to load balance. You might also use them to load balance in between containers. And realistically speaking, here's a container environment. Now, what do you do if you need speed and performance? Well, we might do something like this. We might actually have a network load balancer. And we might have several that load balances between several application load balancers. And then underneath that, we could have multiple microservices or servers. So let's just call it MS. We'll assume they're microservices. And not that that's an official thing, but we're just trying to make something to make this diagram. And by doing that, the application load balancer could load balance in between these microservices, for example, with a great degree of intelligence. And we still have the speed of the network load balancer, so we can do this as fast as we possibly can. And that's common as well with load balancing. So these are what load balancers are. Okay, we're back. Hope everybody enjoyed the discussion on load balancers. If you did, let me know. Let me know you did. Maybe a hashtag load balancers in the comments section below. But I wanted to take a short break to see if anybody had any questions they'd like us to answer. And if not, we'll obviously get back to the content, but I'll give you a minute. And while I wait to see if anyone asks questions, I want to remind everyone that there is a free e-guide that goes along with this. And that free e-guide is available for you to sign up for. It's about 550 pages to help you pass the Google Professional Cloud Architect exam, since this is a Google Professional Cloud Architect bootcamp. I also want to let you know that tomorrow at 11 a.m. we're going to have a discussion live on Zoom, how to become an architect. We'll talk about what does a cloud architect do, the real cloud architect skills, how to get hired, for example, when you lack experience, how to get past the HR people that would tend to auto deny you. So we'll be talking about those. So, that's good. Seems like people are learning about load balancers by the hashtag load balancers. Which makes me very happy. So I'll give it another 30 seconds to see if there are any questions. If not, maybe register for our webinar. Maybe give us a like if you're having a good time. Subscribe if you're learning something, and hit the bell to be notified of some new stuff, because we have a new video every day to help you in your architecture career. Well, maybe give me a hashtag Google Professional Cloud Architect so I know you're awake, alert, and oriented. And Chris, let's roll back with the content. Now let's talk about connecting to the cloud, that wide area network. We're going to discuss it a little further. And we're going to discuss our 2 architectural options and how they are different. I previously discussed what a private line is, and here's the way they typically operate in cloud computing. You typically have your building, And what you typically have is you have a switch or a router that connects to the cloud provider. I'm going to call it a router, layer 3 switch router, whatever you have. You typically connect to a location, which is typically called a point of presence. And inside of the point of presence, you basically have your customer edge equipment, which is your stuff. And you basically bought this connection. And then they typically have what's called and then they typically have the provider equipment, the provider edge equipment. And then typically, of course, you've got the cloud provider. And typically the way this works is your cloud providers are going to have very big, fast connections to these internet service provider points of presence. And you'll typically buy a wire from you to this this point of presence, this wide area network point of presence location. And ultimately what will happen is you'll have to get a wire that connects your switch to the provider switch, which is called a cross connect. So this is your private line type environment for the majority of the cloud providers. And that's why I'm not using any specific vendor terminology here. I just want you to understand the way most cloud providers do this. Now, what you have to understand is this. This is what you bought. So if this was a 10 gig link, you're guaranteed to get 10 gigs all the time. If this link is 2 milliseconds across, it's going to always be 2 milliseconds across because basically you bought a wire, even if it's this convoluted wire sort of thing. Now let's compare, and this is a private line. Google's got its own name for it, which we'll call it, but this is what we're really talking about. It's a private line, and this is what Google calls a cloud interconnect, realistically speaking, but private wall line. AWS calls this a direct connection. Azure calls it express route. The marketing people really make up some funny name for a private line. Now, the alternative we have is basically a VPN, and I'll talk about how that would work. So let's say we have a campus over here, and we now want to connect to the cloud provider. Now, we are connected to the internet. In this particular private line environment, and I'm going to draw a little line between the top and between the private line architecture up top and the wider and the IPsec tunnel beneath us. Now the cloud provider is also connected to the internet. And what we do is we use our routers, and basically what we're doing is we're typically creating a VPN, which typically is secured with an IPsec tunnel. And now what happens is we're using the internet as the connectivity between us and the cloud provider with an IPsec tunnel. Now, the key to remember here is you pay for this. So if you bought 2 10 gig links to the internet, this means you have 2 10 gig links to your internet service provider. Now, it does not guarantee that the internet has 10 gigs available even to get your traffic from point A to B. You only get and buy that connection to the internet. The internet is what's called best effort traffic, meaning if it's available and there's space, your traffic will be sent, meaning if there's not, your traffic will just get dropped. So the key to remember with the VPN, it's very elegant and easy to set up because we probably already have internet. The cloud provider has internet, and we just create this tunnel, which is typically limited to a couple gigabit per second. So it's not going to be the fastest link. And it's hoping that the internet isn't busy. So you can't use this for any mission critical traffic. Now here we bought a guaranteed level of performance, throughput, and latency with our private line here. So this gives us different options. So understand we need some connection to the cloud to be able to access it. And these are the 2 primary architectural options. So we also need to talk a little bit about the domain name system. And the domain name system is going to be a critical component of networking. And its domain name system is, realistically speaking, only doing one thing. It's translating a friendly name into an IP address. So it's probably very easy for you to remember www.google.com. I'm sure it is. but it would be pretty hard to remember the IP addresses of certain businesses. So that's typically why businesses and organizations use DNS. It provides the name to IP address matching. And Google has their own DNS, and it is a high availability DNS system. It's managed by Google. It's fast. It's reliable. And it's going to be there for you. So Google has that. And for advanced traffic management, they offer something called Traffic Director, which will provide dynamic routing for service mesh deployments and really does provide some optimal performance and availability for microservice-based architectures. But I want to make it clear, if you only use Google's DNS and Google were to go down and you had systems on 3 clouds, your DNS for your other clouds or the DNS that might send your traffic to other clouds would go down. So think architecturally, can you use a single cloud provider's DNS services? And Google has great DNS services, or do you need more reliability? Now, networking is not new to people. Even before we had these IT networks, people automatically made their own networks anyway. They would create people in their environment. They knew how to talk to them. For example, at one point, they'd live in a community and talk to each other. At another point, we had the phone and we could call each other. But this networking thing is not new. It's just changed. Now, we can think of modern networking and the internet, and it all started from ARPANET in about 1969, which was the birth of the internet. At the time, the internet was a military tool. It was an academic research tool. I mean, really pretty much the U.S. government, that was it. And a couple other governments, it was a science project. And now at this point, it's probably one of the most impactful innovations of our time. Global data sharing, go to global collaboration, working in any part of the world. So the internet has a massive impact on our lives. And when we're dealing with networking, we can think of private networks, which we purchase internally that we own, and the internet is that global network that we have. So if we think about it that way, we always had networking. So what is cloud networking? Basically, cloud networking is a software version of everything we've already been using, a software-defined version of what we're using. So while the cloud providers have their own networks, the physical infrastructure, the routers and switches that happens, when we get our environment, we're getting a virtual network created in software that's actually running on their servers. So kind of hope this makes sense. So now we're typically dealing now because now we're dealing with networks, and because we're now dealing with softer boundaries of the internet compared to other networking environments, what we're realistically talking about, we may need to use zero trust, which works on the concept of assume that you're breached all the time and don't trust anyone, and microsegment your environment and encrypt your environment, which gives you authentication, which gives you making sure you know who you're talking to when you don't have a man-in-the-middle attack and the data is encrypted so no one can see it, and you've got data integrity checks to make sure the data hasn't changed. So, there's going to be a lot of what we're dealing with zero trust and cloud computing. There are some differences in cloud networking, and that really changes a shift in your perspective because it's virtual. We also have to understand that in cloud computing, the networks are still software and they don't have anywhere near the capabilities that we have in the physical data center. So we're going to be limited in what we can do. We're going to have less features than we would traditionally have because the cloud provider is kind of a jack of all trades that gives you a little bit of everything. In the data center, we can buy specific to networking devices. So keep that in the back of your mind. So AWS has been in this business a long time, since about 2008. Google has been in massive compute for a very long period of time. Remember on that first day I drew a cloud for you? Now think about Google's data centers even before the cloud, making YouTube, Google Search, Gmail, and every other application they run. Millions and millions of servers, you can imagine, are being used to this, let alone the number of servers that are running their AI and their algorithms. So there's just so much going on. So what happened is we moved, in many cases, the data center, the physical data center, to the cloud. So that's what we're dealing with Google's cloud. Now, with regards to the cloud, we also have the concept of a content delivery network. And Google has a content delivery network. It's an excellent content delivery network. Of course, there are other content delivery networks that you can think of. And let's talk about why we will use a content delivery network and actually what it actually is. So let's whiteboard this. A content delivery network is going to be a network of servers that a provider has. For example, so let's say we've got a provider over here. And the way the internet works is there's going to be all these little points of presence all over the world. They're called POPs. And I'll show you what typically happens in these points of presence. And I'll show you why we often use content delivery networks. So the internet will have all these points of presence. And what's going to be coming inside of the points of presence? Other internet service providers. They're going to use this as a hangout, meet up kind of room. So, for example, let's say, and these are all going to be separate ISPs. Bear with me 1 second to draw it out. So let's say we've got this one. I'm going to use this one here. Let's say we've got another one over here. And then let's say we've got another big provider over here. But in this case, so let's say this was AT&T. And let's say this was Verizon. And let's say this is NTT, Nippon Telecom, a Japanese telecom. Oops, you can't really see that. So let's just call it an N. So what happens is all these providers have connections to this building. And all that's necessary in the building for the providers to talk to each other is running a cross connect, or it's just a cable to do this. So that's typically an internet point of presence. Now imagine this. Now you've got a content delivery network provider. So let me call it CDN. Now the CDN has a couple of things. One is they have fast networking connections. Let me just make this big, to all these internet points of presence. So they've got a fast network in between them. And in addition to the fast network, what they do is they put caching servers. So we're going to put a caching server in each point of presence. I'm going to call it CS. And by doing this, let's say you're a Verizon customer. As you get your traffic, let's say you want to access something. So you want to access something. So you go to a website. Because you're on Verizon, you hit your Verizon Internet Service Provider, but your website's hosted on AT&T. So what typically would have to happen is your routing would go to back to AT&T where the website's hosted. So you would go to Verizon. This would be your local point of presence, and all of a sudden you would go from your website, Verizon site, all the way to the AT&T site, and then your traffic would come back. So what's going on here is we're using up AT&T's bandwidth to go from this point of presence all the way there. Now, AT&T wants to save as much of this network as possible, and you don't want the latency time of reaching AT&T. So let's say we've got the user who's on Verizon, and all of a sudden they hit the Verizon content delivery network, and your information is already sitting here on the caching server. You don't even have to leave your internet point of presence and have to go wherever the source of the server is. So that's why we typically use content delivery networks. We use content delivery networks for two other reasons, and we'll talk about what those reasons are. Here's the first reason. So let's say here's our server. And let's say, here's our cloud and the server's well, let's not even worry about where the server's hosted. But let's say our server's here. Let's say we've got an Athens location. Let's say we've got a Neperamos location, which is my village in Greece. And let's say we've got a Crete location. Yeah, the island of Crete. You may have heard it be called Crete from non-Greek people. So let's say I've got a user in Athens, and here's the CDN. Now, obviously, it's not going to be one thing. It's going to be these caching servers. So all of a sudden, I've got a user in Athens. Let's say this is Nikolaos. And Nikolaos wants to get access to a web server. So Nikolaos is the first person today to want to access that web server outside of Athens. So Nikolaus goes to his browser and he goes to the web page. It's not located in the Athens Content Delivery Network, so it goes all the way back to the source. The server then responds, and then it's seen by the Content Delivery Network, and it's cached at the Athens location at the Content Delivery Network, Athens cache. And now the information is here. Now Nico's finished his work, but now we've got someone else that wants to use the system. We've got Dimitri who wants to use the system. So now Dimitri wants to use the system. He's also in Athens, Greece. Dimitri goes on his browser to the same website that Nikolaus just went to, and immediately his traffic hits the Content Delivery Network point in Athens and is immediately sent back to Dimitri. And now Aguilo wants to use the system, so Aguilo uses the system. He's also in Athens. He hits the local Content Delivery Network and his website come back. So what you can see is not only did the web server only have to handle one web request out of the 3, but the latency has also been reduced by storing it locally at the Athens part of the Content Delivery Network, which means the user experience was better and there was less work on the server, which means I can scale better. Now, here's the other thing that we want to talk about. So let's assume we've got a bad guy, bad girl, a couple of bad people that are trying to cause an attack, and somebody launches a DDoS attack towards that web server, and they send a bunch of 50,000 TCP SYN connections very quickly, and all of a sudden it hits the NetPedamost part of the CDN, and the NetPedamost part of the CDN says, this is bad traffic. I'm not going to send it to the server. I'm not going to overwhelm the server. I'm just going to drop it here. So from a distributed denial of service protection, we get a lot of mileage out of our content delivery networks. So I hope that makes sense why we use content delivery networks. It enhances scalability. It enhances performance by reducing latency. It decreases server costs. It decreases the wide area network transfer costs in many cases, and it helps protect against DDoS attacks. So all in all, big wins for content delivery network. So let's talk about Google's network. It is global. It serves billions of users. It supports internal applications, public applications, whatever you need. So public applications would be things like Gmail and YouTube, and customer applications. And this is connected to everybody. Now, Google also has a lot of data centers. In fact, they've got 22 data center regions, 67 zones, which are data centers inside of them, 140 internet points of presences, and 800 global cache nodes. So they've got a lot of cache systems that are already out there in a reasonable number of points of presence. So they've got their own network. And it's a big network, and they've got a lot of infrastructure. And when they're selling you cloud computing services, they're selling you access to a network and a data center, which is cloud computing. We talked about what are points of presence, and Google has edge points of presence as part of their data center. And, we talk about how the user requests will be routed, and they will be routed, typically speaking, to the place with the lowest latency. So there is that. Now, Google as a global network has what you call a Juniper network fabric. And that's Google's custom networking hardware system. Juniper provides immense bandwidth and scalability. It delivers more than 1 petabyte per second of total bandwidth. And that allows 100,000 servers to exchange data at 10,000 gigabit per second each. So it's a pretty big, pretty powerful network. This network throughput is so big that it could read the entire contents of the library of contents in under 1/10 of a second. So that's how much data you can push on it. But again, you got a lot of users pushing on it. So don't exactly think it's that big and that scary when you consider the number of users using it. So we can talk on Google's network. We can talk about the Andromeda virtual network stack. And that is Google's software-defined networking stack that abstracts the underlying in-network infrastructure and the data center hardware. It ensures secure, private, and efficient business operations for Google and its cloud tenants because it's keeping everybody separate. It's all software-defined networking. It's all in software. And Google likes to say that their iterative improvements with Andromeda have led to significant performance gains, such as a 3.3% increase in virtual machine to virtual machine network communication. So that's pretty big. They're constantly, obviously, improving their network. As they need more and get more customers, they're going to constantly have to keep upgrading the capacity of the network. Now, generally speaking, with networking, we should encrypt our data often. If we're on a public network, we have to encrypt our data. And if we're on a private network where no one has access to it, is it questionable? Do we need it? Questionable. But we might still want to encrypt it to make sure the endpoints are who they claim to be and that the data hasn't been changed along the way, and provide a non-repudiation trail. So we might want to do it anyway. So think about that. Now, Google will encrypt and authenticate all network traffic in transit when it flows outside of the boundaries and it's not controlled by them. Like I said, you don't necessarily have to encrypt internal traffic data in the private network, but once it goes to the internet, it must be encrypted. Now, generally speaking, security professionals, we would question the lack of encryption for data in transmit, potentially on the Google Cloud in a multi-tenant environment, but the reality is we can encrypt our IP traffic across their network anyway. So by doing this, we're there. But generally speaking, keep that in the back of your mind. If a cloud provider is not encrypting things, a packet sniffer or protocol analyzer could see traffic, and we're subject to things like an ARP poisoning attack or an ARP cache poisoning attack. So there is that. Now, it's very hard to encrypt an entire enterprise network because that will take a huge impact on speed and performance. So make sure your data is actually encrypted. Google provides what's called encryption in transit, and that's with something called Google Front End. And that's going to be a reverse proxy that's going to protect Google's backend services. When a user will send traffic to Google, it'll reach the nearest edge node, and then it'll be routed through the Google Front End. And that way the Google Front End can authenticate the user. They can ensure the integrity of what's being sent, and they can use encryption in transit. And that's typically TLS security, specifically boring SSL. Let's talk about protection inside of Google's boundaries. Inside Google, we may have data that needs various levels of protection. And the data that remains inside of Google's physical boundaries is generally going to be authenticated and tamper resistant because it's already inside of the system. But when data leaves Google's physical boundaries, now the network is not completely trusted. It's considered semi-trusted, and therefore Google will enforce authentication on encryption in transit, which is great. Now, with regards to encryption in transit, let's talk about some application layer security. So Google will use remote procedure calls for service-to-service communication. And this means these calls are going to be, these Google remote procedure calls are going to be authenticated, which makes them tamper resistant because you know who they actually are. And they're encrypted in transit using AES encryption for any calls leaving the physical boundary. So within Google's boundaries, the focus is authentication, ensuring that the data is tamper evident. But when it leaves it, it's making sure that it's encrypted. So let's talk about encryption in transit. Let them think about internal security controls. Google will attest and rigorously test their internal security controls to prevent any kind of insider threats. And you have to hope they are, but you have no control that they're doing what they say they are. Google maintains high levels of audit and compliance of these controls. Absolutely. So let's think about some additional security measures. We may have multiple tenants on the same environment. And we'll talk more about tenancy and virtual machines, but I'll give you a little information on what I mean by that right now. In the cloud computing environment, we might actually have a server. And let's say this is the physical server. Now, the server is going to have a hypervisor, and that's going to be what's going to separate you from your clients. Now, that means that you're going to, in most cases, have multiple companies here. So let's say this is a Cindy company. So her virtual machines, or Cindy's company's virtual machines, are going to be here. Now, Cindy has a nemesis. We call her Caddy. Caddy seems like a very nice cat, but Caddy comes every day and Cindy is terrified of her. So that's Cindy's nemesis. Now, we could also have a cat. Let's say it's an orange cat. I've been meaning to get an orange cat or an orange Maine Coon. So let's just call this the Maine Coon that we don't have yet that I would like to bring home, but I don't think my cat would be happy about it. So I haven't done so yet, but I've been meaning to do so. So let's say we've got these 3 different businesses or on the same system. In theory, and meaning most of the time, realistically speaking, Cindy should never be able to see Caddy's traffic, or Maine Coon shouldn't see Caddy or Cindy. They are logically separated by the hypervisor. Now, if the hypervisor was attacked, the concern is always the virtual machine escape, that you could leave Cindy, hack the hypervisor, and go into Caddy as well as the Maine Coon. It should not happen. But under high security circumstances, a company may not be on a multi-tenant server. They may mandate that the server is dedicated to themselves, because these attacks shouldn't be possible, but they still could potentially occur. So I kind of hope that makes sense. So make sure you're using encryption. Make sure you're securing everything that you possibly have that's under control for you. Okay, well, we are back. We've been having what I think is fun, but then again, this is the kind of thing that I actually enjoy in life. So I hope you are all having a good time. Now we're here to answer any questions. It looked like 1 or 2 popped in, so we definitely want to answer that. And if you have any questions, let us know. But Chris, I saw 1 or 2 questions come in. If you want to bring them in. Could I elaborate for the audience the differences in load balancing strategies, specifically when it comes to managing access across cloud native services, internet facing endpoints, and cloud adjacent services? So why don't I do this in production by Inc? What if I walk through every kind of load balancing that we've been using for the last 30 years that exist in absolutely every data center, in absolutely every cloud provider in the entire world? And I think we can do that in about 5 or 6 minutes. And that way you'll understand them all. So let me walk through this from an architectural perspective. I'm going to start with the kinds of load balancing we use and where we use them. Now, the first type of load balancing I want to show you is load balancing between clouds. Now, let's say I had a publicly facing website. Let's say the website is Go Cloud Careers and it's in 3 different clouds. So what I would do is obviously DNS, we would register Go Cloud Careers. Say it, hold on, CRERS.com. And that would be the domain, and we would put that in the domain registrar. And then we would set up a routing policy that says send 50% of the traffic to our data center, send 25% of our traffic to AWS, and 25% of Azure. And what happens is the DNS will run a health check. Data center, you there? Data center, you there? Data center, you there? And if for some reason the data center doesn't respond, we mark it as unhealthy, and DNS will shift the traffic to AWS and Azure. Now, if our virtual machines or containers running our websites are in AWS and Azure and our data center goes bye-bye, the auto-scaling groups in AWS and Azure will be able to auto-scale within 30 to 45 minutes to handle the capacity. So that's one type of load balancing we use. But let's talk about in our VPC. So in our VPC, you're going to have a lot of different kinds of load balancing. You may have a load balancer between virtual machines. This could be an application load balancer, network load balancer, or both. We may be using an application load balancer to load balance between containers, for example. We might be using an API gateway, which basically also does load balancing to load balance between microservices. And we might be using a network load balancer to load balance between our virtual firewalls that we're going to use to connect our VPC to the internet. But and there's a reason I want you to show you the rest of it is it's all load balancing. So if we go to the servers that AWS, Azure, Google, or the server sitting in my home, you're going to know most of them are going to have what's called a RAID card in that. And the RAID card is going to load share between various hard drives. For example, if you've got in this drive if you've got 6 drives, and each one is 4 terabytes, you can have this basically have spread the load across the drives. So if you have 6 4 terabyte drives, you'd have 24 terabytes together in RAID 0, for example, and you would have 6 times the speed. Now, when you go to the cloud provider, and we're going to get into object storage, and block storage and file storage, But when we deal with the file storage the block storage, this virtual hard drives, here's what's going to happen. They're going to sit in these giant boxes, which are going to have RAID cards, and each RAID card is going to be connected to a whole bunch of hard drives. So we're going to see load balancing there via the RAID cards. But when the load balancer connects to the network, we might have 400 gig links or 4 800 gig links or whatever it is that we're using to connect the storage area network to the network switch. Now, we'll typically place them in something called the link aggregation group, and the switches and the devices will actually load balance between those links. But we might also use BGP or a routing protocol to load balance between this link or this link in our data center. But it's not just there. I mean, load balancing's everywhere, because now let's go break it down and go to a server. Modern server, let's say we have two 64-core CPUs in it that we use in that virtualization. Guess what? We're going to load share across all of these CPU cores. The hypervisor will typically take care of that. Now, if you open up the server, you're going to see DRAM and banks, and we're going to be load sharing across them too. And if you're dealing with an AI computer, you're typically going to have a PCI interface that's going to load share between the various graphics processors inside of that same device. And to be fair, if we even connect our data center to the cloud, guess what? We might have 4 links up here from Verizon and 4 links over here on AT&T. And what we might do is put one subnet on the top link and one subnet on the bottom link, and then an aggregate route as backup for the top and bottom. And that way we could load share for these links. So what we're really doing here is we're basically load sharing throughout everything we entire do. It doesn't matter whether it's a microservice, a server, a network port, a network switch, it's all the same load balancing. So I kind of hope this. So here's the things that I want you to think of for load balancing to work. Something has to track these connections, right? So in DNS, we use a health check. In a physical load balancer, we use a health check. Across these links, we might have a layer 2 protocol. We might detect when a laser goes down. It could be keep alive is missed and a hold timer is missed in a routing protocol. So we always have to find and to detect a failure. And once we detect a certain number of failures, we need to know when not to use that. That's realistically speaking the components of load balancing. And why do we use load balancing? Well, I can load share across 6 hard drives. I've got more speed than if I only have 1. I can load share across 8 GPUs. I can do more machine learning or AI than if I had 1. I'm in my data center and I want to load balance across virtual machines. Well, I don't have a single point of failure if I have multiple virtual machines. So I can combine capacity and performance. So I kind of hope that answered your question there. And it said, perfect. This is exactly what you thought it was looking. Wonderful. I'm glad I got it. Can I describe the types of private lines to connect to a cloud provider? So, Darnell, let's whiteboard this. I like the question. So when it comes to private lines, realistically speaking, it's going to be one of 2 ways. And in reality, you're never going to know the difference. But let's walk through it. So you could have something that looks like this. Let's say you had fiber buried under a city. Let's say this is your building 1. And let's say this is your building 2, and it is 50 kilometers away, but you own them both. Now you could own, and truthfully, a piece of fiber optic cable under the ground. And what you're basically connecting to is you're connecting to an Ethernet card. You're connecting to a wire, and this is going to be an Ethernet handoff in both places. Now, the next way that you can basically get this is, and all this stuff has been around for a while, is you can connect to a phone company or a wide area network provider. And one of the options is they can create a switched wired connection for you where it'll just feel like an actual wire. And it'll be a wire that you plug into building 1 and building 2. This is your traditional private line. Now, in the old days, this was signaled electrically. When I started, the electrical engineers were the network engineers. I mean, all this stuff was signaled electrically in switches that opened and closed physical circuits. Now, what it is in today's world is, in most cases, the way these wire, and then I'll map it out for you. So let me just get rid of the fill. So what it is in today's world, and I was one of the people that helped design many of these things when this first became possible. When I was working at Riverstone, Luca Martini was at Juniper, Footer and my friend and I were working on this at Riverstone. It was the creation of what was called the pseudo wire. So what you would do is you would connect to the service provider's wide area network via just standard Ethernet cable or a fiber optic Ethernet cable. On the far side, you would connect to the service provider's network. And inside of their network, it looked something like this. It was an IP network, and most of your private lines now are signaled this way because it's just so much more convenient. You've got a typical underlying network, say it's OSPF, IS, and by ISAS I mean intermediate systems to intermediate systems. The old CLNS routing protocol that's widely used for routing in today's world because it scales really well in the way it sends its LSAs. So what happens in today's world, many of these private lines look like this. So what happens is you basically buy what's called a pseudo wire. And what's happening is you connect via a real cable here, you connect via a real cable here, and then you're buying a virtual wire across the company's back, across the IP provider's backbone that's basically routing and electrical engineering signals sent into MPLS to be tunneled across the backbone. So that's typically there. So what does it really look like when we actually bring this into the cloud provider? Well, we're here in our campus or wherever our people are, and we ultimately buy a link to a point of presence. Now, a point of presence is a place where a whole bunch of internet service providers and wide area network providers actually coexist together. So AWS would call it a direct connection center. I think Azure would call it a point of presence. It's all the same thing. So what happens in the point of presence is you're going to have a device like a router or switch, your device that sits there. And the cloud provider is going to have a big giant or a bunch of connections that goes back to the cloud provider. And that's going to be your cloud provider. And this works for AWS, Azure, Google. It's all the same. And what happens is the cloud provider has their switch over there. So what happens is the provider has a switch that's connected to their network. You buy a wide area network link between you and this point of presence, direct connection center, meeting center, what have you. And then what happens is you get a letter of authorization for where the direct connection facility, the point of presence, is allowed to run a cable between your device and their device. So what happens is you've got a cable between yours. It's called a cross connect. And that cable, that cross connect takes you between yours and theirs. So now you might say, but Mike, what's going on? This looks like a big pipe over here. Are a lot of customers going to be on this? The answer is yes. So what you'll do is you'll add what's called the VLAN N802.1Q tag. So you will have the blue tag. Another customer that will be on here will say have a different color tag traffic. So this traffic will be, and that's how the provider will separate your traffic as it crosses their network. So this is exactly the architecture of how these private lines. But if this is a private line that's signaled via MPLS, if there's a private line that's just a wire, in the reality, it's the same. So basically you have an Ethernet private line, which is what you're using to connect to the cloud providers now, in most cases. Hope that helps. Now, if you didn't want to, and Darnell, if you didn't want to use a private line, you could obviously use an IPsec tunnel, a software-defined WAN, a SASE WAN. But in this case, we were asking about private lines. Well, I don't see any more questions. There were some good questions. I love to see these kind of questions. So we have one more video, and then after that, Leo's going to get a little geeky and do some labs with you. So I hope that should be lots of fun too. So let me know you're having a good time. Give me a hashtag Google Professional Cloud Architect. If you're enjoying the content, give it a like and signal the algorithm to send others here. Maybe subscribe and hit the bell because I'd love to see you in another video. All right, Chris, let's roll back to the content. Now we're going to continue our networking discussion, and we're going to begin with the network service tiers you can get in the Google Cloud. So Google offers you several performance tiers, realistically 2, on how you can send your traffic through the Google network. And which tier you use will determine how much performance you actually get, what your latencies could be like, but there'll also be a higher cost to get better network service and a lower cost to get reduced network service or more normal network service. So we're going to talk about what those 2 service tiers are, but before I do, it's going to be necessary to talk about internal routing and external routing. So let me whiteboard that out for you. In internal routing, we have an environment that we own. So let's say this is our data center or the Google's cloud data center. I don't care. We're just going to, I'm putting on one of the links a data is just data center, so we can use it. And it could be Google's data center. It could be our data center. It really doesn't matter. The key here is in a private cloud, and we're going to use this to explain the service tiers in a minute. Everything in this underlying infrastructure we own, which means if we know how much traffic is going to be coming into our systems, we have the ability to make sure that the routers can handle the traffic and all these links that we have are big enough to handle the traffic. And we can capacity plan and always guarantee that our traffic is going to get through our network at a certain period of time. This is private data center. This is the cloud networks provider. This is all networks that are owned by a single entity. They can guarantee performance if they want. Now, in this separate environment, I actually drew internet routing. So let me call this ISP-A. And I'm going to draw this picture as ISP-B. And then I'm going to give you show you ISP-D. And then you're going to see ISP-C. And here's the reason why I want to show you this. Internet traffic is considered best interest, best effort, meaning there's no guarantee the traffic will ever get there, and there's no guarantee of the performance. It's best effort. Now here in a private network that we own, we can guarantee it because we can make sure that we have the capacity for everything. It's all under our control. But the internet is a collection of thousands of internet service providers that are connected to each other. And the way internet routing is, let's say we've got a user, and this user is a cat. Let's call it a Maine Coon cat. And in this case, we've got a user that wants to use the internet that is a tabby cat. And the tabby cat wants to talk to the Maine Coon cat. So the way internet routing is, if the tabby cat is connected to the internet service provider C, and the Maine Coon is attached to internet service provider A, what happens is the tabby cat goes to their local internet service provider. It says who has a route to the network where the Maine Coon would be, and it looks in its routing table and it says, I have to go to ISP-D. So it forwards the packet to ISP-D, and ISP-D says, who has the subnet? And it says, oh, I'll send my traffic to ISP-A. But see, ISP-C, ISP-D, and ISP-A are all different companies. So because they're different companies, the problem lies in the following. How do I guarantee is this link between internet service provider C and D could be fully saturated, or it could be small, and it may not be enough to meet the needs. Or let's say the link between the tabby cat and her internet service provider is strong, and it gets there fast. And even the link between the internet service provider C and D is great. We have no guarantee of the performance of ISP-A. So when you understand that, you'll understand that internal systems we can guarantee because they're under our control. Whereas external systems that are not owned by us, we have no control. So what does this mean? It means Google offers a premium tier of networking service that's going to leverage much of the Google's private network, and it's going to use more intelligent routing, and I'll walk you through it. So normal routing is a router sees the fastest opportunity to dump its packet, and it sends it to the next router. That's normal routing is called hot potato routing. Google can use cold potato routing, which is a little bit smaller, which is going to keep it on its network longer until it reaches the best place to give it to the internet. So that's what we're talking about with the premium service tier, and I will actually whiteboard it out because I really want you to understand those. Okay, so let's whiteboard this out. Now, you'll recall that I said what's under our control, we can guarantee the performance. But the internet is out of our control, so we can't guarantee its performance. So your VPC is obviously connected to the Google data center. It's in the Google data center. So I'm just going to draw a little link as if it looks like it's linked to the data center. It is. It's sitting inside the data center, but just for easy purposes. Now, this data center is the cloud provider's data center, and it's under their control. Now, this data center has the ability is connected to the internet all in so many different places. It'll have many internet service providers. There's many points of presence and internet peering points where Google Cloud is going to be on the same way all cloud providers would be. So there's two ways the data could be sent. In hot potato routing, which is going to be more of a standard tier, which we're going to talk about next, if we have data that needs to reach something on the internet from our VPC, it's going, or an internet user would be trying to reach it, it's going to get to the internet as fast as possible, which would be in San Francisco, and then route it all across the internet to where the user is. And let's say the internet here is in Palm Beach. This would be hot potato routing, where this router passes it, that goes to this router, and then the internet routes it to the end. That is standard routing that you would get in more than the normal performance tier. In the premium performance tier, Google does something very cool. What they do is they route their traffic all the way over their network where they can guarantee the performance, and then it actually leaves the network closest to the end user. So if I have a user in Palm Beach, and this website set up at the west coast of the U.S., if the traffic is going to take the entire Google network where the performance is great, and it's going to only leave the internet and hit the internet in Palm Beach where the user is. So typically speaking, you could get a lot better performance as traffic would go in and out in the best path. So that's typically what you're getting with these premium network service tier, efficient routing. Now, the premium network service tier also provides some additional cloud networking features, global load balancing, and it gives you the ability to provide better performance. So now let's talk about our standard tier. Now, this is going to be cheaper, but you're not going to get the same performance. This is going to use that hot potato routing that I talked about. I'm going to show it again just to make sure you've got it. And in this case, you may also not have access to all of the networking features. Here we've also got lower performance. So please understand, cloud networking has already reduced features from what we had. So, if you're in that standard tier, you're going to get a lot less features potentially that we normally had and lower performance as well. And let's go back to show you why. In the standard performance tier model, instead of that intelligent routing all the way across the internal network to get to the closest ISP to the user, now, and that would be the cold potato routing, now we're using hot potato routing. So here's the normal service. Leaves your VPC and finds the closest point to get to the internet, leaves, regardless of where your internet user is. So that's why this is going to be a lower level of performance. So if we think of it, with the premium, we get better performance, we get better routing. With the standard, we get lower network performance. We get a higher service level with the premium, 99.9%. 99.99%. Which is pretty good. That means 52 minutes of downtime per year, approximately. By comparison, on the standard tier, we get 99.9% availability, which is much less availability. So if we need high performance, a global footprint, and an experience and better networking features, we're going to use the premium tier. But if we're a smaller organization and we're willing to reduce some network performance, then we could use the standard tier. So let's now talk about the virtual private cloud, subnets, regions, and zones. And we introduced the concept earlier, and we'll talk about it some more. So the VPC is effectively your virtual private data center. And that's where you're going to put all your cloud stuff, like your virtual machines. And what creates these virtual private clouds, your virtual private data centers, your virtual hotel room inside of a hotel, if you will, is it's really a software networking functionality and network function virtualization. And this is basically software that creates software versions of traditional networking things. So what you'll see in any VPC or VNet for the most part are things like load balancers, access lists, routers, routing type features, and typical networking things. And because nothing can talk to each other without a network. Your virtual machines wouldn't be able to talk to each other without a network. The containers in Kubernetes couldn't talk to each other without a network. Nothing could ever work without a network. So your VPC, you're going to put a lot of different things. So when we talk about a virtual private cloud, like I said, virtual private data center, let's talk about what you're going to get. You're going to get load balancers. And you'll have that. We'll talk about we'll talk about every technology you need to know for this Google Professional Cloud Architect exam. You'll have multiple WAN connectivity options to connect to other places, other clouds, your data center, what have you. And that means you'll typically have a private line, some form of a cloud interconnect or a dedicated interconnect. We'll talk about these kind of things, the dedicated internet connect. And you have VPN tunnels like an IPsec tunnel or a TLS tunnel. Now, in Google, VPCs are global resources, meaning they're not going to be tied to a specific region, which is a geography, or a zone, which remember is just a data center in the Google Cloud. And it will provide project boundaries. So VPCs are going to be created within projects, and they won't typically allow cross communication. And they definitely don't by default. So the point is, we put our VPC, it's a boundary. It's a segmentation or a micro segmentation of our system, depending upon how many of these we use. Now, of course, if we're dealing with routing, you'll have to put your servers in a various subnet, and your network will still have a global site or range or classless interdomain routing range. So that you'll have in this particular environment. And of course, regions are a large geographic area, and a zone is a data center inside of a region. So a region is going to be that big geographical area, and it'll contain multiple data centers called zones. For example, there's a U.S. East region located in Ashburn, Virginia, and there's a couple of zones in there as well. So a zone is going to be an isolated location inside of a region that's going to be usually a single data center. And zones within a region are designed to be isolated from each other to protect the impact or an outage from one zone to another. Theoretically speaking, if we've got one data center and we've got another data center and they're independent from each other, we shouldn't have problems. But do they share networking? Do they share routing? So they're still connected and they can still have problems from one to the other, even though the theory is that they shouldn't. Now, the point here is, you don't want to put all your eggs in a single basket when it comes to availability. So if we have a zone, we have a region which is going to be a relatively large geographic area, it doesn't make sense to put it into only one data center. Split your load amongst multiple data centers, and that way if one data center goes down, you've got another to back you up. And if we had one zone here and one zone here in a non-super high availability environment, but a relatively high availability situation, and the one zone went down because the data center went down, the second zone could use auto-scaling and come up to full capacity, theoretically speaking. So, that's one option, and that's why we're talking about zones. Other providers call them availability zones. They're data centers. Now, let's talk about fault tolerance and redundancy. So if you're building a critical application, you can't have any single points of failure. Many people would say that a single cloud is a single point of failure because there's cloud shares to some degree a common network. There's control planes across that have to integrate to all clouds. So if you had a major network outage, a major hacking event or a control plane failure with the cloud provider, you could be in every availability zone and every region in the world and you're still down because the cloud provider is down. So many organizations use multi-cloud. But the key here is we have to think about everything in higher availability systems. No single points of failure. Redundancy everywhere. So redundancy in your connections to the cloud provider, redundancies in the routers that connect to the cloud provider, redundancies in where your systems are plugged in, and how many circuit breakers they're plugged into, and what your power looks like, and what your cooling looks like. and what your change control processes look like. Because you could have everything perfectly designed, and you could have a user puts the wrong thing on the system, and it can take everything down if they didn't understand the impact of their work. So when it comes to real high availability, we're going to be talking about so many other things, typically speaking. Now, we also have to assume outages are going to occur. So you should plan what happens if this availability zone goes down, or this cloud provider goes down, or this link goes down, or this power supply on your router goes down, and see what the impact is. Now, if it's a router with two different power supplies on two different circuit breakers attached to two different generators and one power supply goes down, you're not out. You get a notification about it. You swap the bad power supply for a new one, but you're still running on the alternative power supply. So we always have to design, you could almost call it outage planning. You have to think of every kind of outage that would occur in your high availability design and then figure out how you would mitigate that. And when you're dealing across 20 different domains, you're going to need an architecture team. So we're going to have to think about IP address planning. And that means we're going to obviously have a CIDR range for our environment. And that means we're also going to have subnets. Now, if the CIDR range is designed elegantly, the routing will be beautiful. If the subnets are designed elegantly, the routing will be beautiful. If the subnets are designed improperly, we will always have problems. So we have to be careful how the subnets are there. This is going to be more the work of a network architect to really be thinking about subnet planning and route planning ahead of time, but keep that in the back of your mind. But we'll have to create a CIDR range, and then we'll have to create a subnet. So for example, I know I did this a little earlier, this could be a CIDR range, for example, 192.168.0.0/16. So this by itself, this block, has about 65,000 IP addresses inside of it, depending upon how it's subnetted. So this is going to be a CIDR range. And then this gives us, which all the IP addresses are going to start from. I'll draw them out for you. If they were all going to be in the single CIDR range, which they couldn't be, and I'll show you why they couldn't in a second. But this means that this range will give us IP addresses of 192.168.0.1 all the way to this broadcast address, which would be 192.168.255.255. So that's a lot of addresses, and that's the address range. But a subnet might be this, 192.168. Let's say 1.0/24. And then another subnet would be 192.168.2.0/24. And another subnet would be 192.168.3.4 or 0. And I could do this all the way to 255, realistically, or 254. So /24s. And I could do that. But, oops. And I could do that. And I've got a fair number of these that I'm actually talking about. So this is really what we're actually talking about. The kind of ability to take this big thing and then chop it into many other different things. And these subnets that I've given you could also be chopped down into other things if we went into smaller subnets for WAN links. And that's how we're going to start with a CIDR range or a big address block, and it'll be subnetted down so we can do things properly. Now, I'll show you what I mean by good addressing, and I'll show you what I mean by bad addressing. This is going to be good addressing, and I can show you why. In here, we have 192.168.0.0/16. And over here, we have 172.16.0.0/16, and we have a link between them. This is a beautiful situation. And the reason this is a beautiful situation is going to be as follows. All that needs to be sent for this traffic to reach each other is this route has to be sent, let's call this Let's call this our data. Let's call this our range on GCP. And let's say this is our range on AWS. But ultimately, when we send our BGP routes, the Google Cloud or your VPC on the Google Cloud would need to tell, realistically speaking, AWS of only one route, the 172.16.0.0/16. And it's going to be smooth and easy to set this up. And by comparison, AWS would only need to tell the Google Cloud about, or your VPC on the Google Cloud about a single route. And it's going to be 192.168.0.0/16 will be the route that's sent. This is simple and this is so elegant. And when we have this, we never have any challenges. Here's where things go wrong. Let's create another one. Let's put this here. See if this thing goes away. Okay, so here's where people get it wrong. They do this 192.168. Let's move these addresses, and I'll show you where we get in trouble. So if in here they put a 192.168.1.0/24, and then they get a 192.168.3.0/24, and then they get a 192.168.4.0/24. And let's say at the same time, somebody also used the 192.168 segment over here, and they decided to just divide it in a way. But over here, what they did is they did 192.168.2.0/24, and then the 192.168.5.0/24. Well, we have a problem now. And the problem becomes is this CIDR range, which you really want to send this 192.168.0.0/16, you can no longer send that route over to Google because Google also have routes in that same domain. So what this means is you'll ultimately have to send every single route along the way. And the cloud providers have limitations on how many routes you can actually send them. And when you do it this way, what will ultimately happen is you'll get too many routes in the routing table or the memory of the routers, potentially speaking, and then they crash. And then your entire network falls apart. And it used to happen much more with weak or inefficiently powered routers. So we have to be mindful about how we actually address these things. Okay, so that's elegant addressing versus non-elegant addressing. Again, if you're going to be a cloud architect, and that you're going to have to know how to create an architecture team and get the right architects here, and the network architect can help you. So your CIDR, your classless inter-domain routing will give a range, and then the subnets will be something inside of that range. If you're new to subnetting, we've got some subnet webinars. My team will pop that in the chat box for you to learn more about subnetting. Now, inside of your organization, you're going to be using private IP addresses. The same private IP addresses you would use in a data center. And they are the RFC 1918 private IP addresses, which are going to be the 10.0.0/8, which we talked about earlier, the 172.16.0.0/12, and the 192.168.0.0/16. Now we have to understand that we have private addresses. They're not going to be reachable from the internet for the most part because private addresses can't be routed on the internet. So we want to use private IP addresses whenever possible, and we want to keep our intranet subnets protected from the internet. Now, the only time we ever want to expose something to the internet, ever, is if it must be reachable on the internet. And if that's the case, then we need to do a lot to go protect that system on the internet, and ideally keep it out of our internal systems with a good, strong demilitarized zone, for example, for the security professionals amongst us. Now, Google Cloud, like others, also restrict certain IP ranges. They have certain IP addresses that are reserved for Google's APIs, services, and internal functions, so you can't overlap with them either. Now, we're going to talk about traffic types on the internet, and basically we're going to have egress traffic and ingress traffic. So let's talk about ingress and egress traffic. Ingress traffic is traffic that is coming into our domain or our network, whereas egress traffic is what's leaving our systems and going out. So ingress is coming in and egress is going out. And that's going to be ingress versus egress traffic. Now, you have to understand that certain cloud providers allow certain types of traffic for free, certain types of traffic that they charge for, and this changes constantly. So you're going to have to check. Generally speaking, ingress traffic is free of charge, and egress traffic, depending upon where or what kind of egress traffic, they typically charge you for. So if you think of an external website, that would be all egress traffic for the most part. The ingress is the request for the website, and the traffic going out is egress traffic. So you have to understand that and evaluate it and look at the specifics of your situation. Now, for anything to work ever, you need a network. And what routers do is they route traffic from one subnet to another. And we can use them to route to egress outside of the system. We can use them to route across our systems. So in networking, we're going to have a couple of different kinds of routes. And remember that routers look in their routing table to determine how to get traffic to its destination. So let's draw it out. Let's talk about the kind of routes you'll typically have inside of the Google Cloud. So in this environment, what you can see we have a network. And the network itself is going to have some routers. And the routers themselves will have what's called the routing table, which is going to be a map to get to the subnet. And there's going to be typically two kinds of routes you'll have in the routing table. And you'll have something that's what you'll see called the subnet route. And it's going to look like 10.0.0 /24. And let's call this link GE0. So let's assume that we had a gigabit Ethernet link on this router. And this link itself is called Gigabit Ethernet 0 in the routers world. And what you'll see is you'll have a routing table that's going to have two kinds of routes. And it's going to be, how do I reach a specific subnet? And where do I go when I have absolutely no idea where to go? So that's called the default route. And default route says, if you don't know where to go this way. So that's typically reserved for internet connectivity. Now, there's other times where we might use a default route for everything and then have routers that have more intelligence. But for the most part, a default route is used to connect you to the internet, because if you don't have a route to it in your external network, it's probably destined for the internet anyway, so just send it to the internet. So that's typically what we're dealing with in environments, is the routers themselves will build a routing table. So let's say this router over here has this route in its routing table. And then what this router will do, it says, if I need to reach the 10.0.0 /24 subnet, go this way. And it'll typically give you the port that it egresses to or the next hop IP address, which in this case will be router 2. Then router 2 will have to look in its routing table, and it too will have a route which is going to send it to the next router. That router will look and say, do I have a route to 10.0.0.0? And it says, I'm directly connected. And what the router will do is it'll do what's called an ARP. Who has the MAC address for the IP address that they're looking for? And then it'll be sent. The host will respond, and then the traffic will reverse its path back with assuming the routes are in the routing table. So that's normal subnet routing. And a default route is when you don't know where to go. So if I know where to go, follow the path. If I don't know where to go, send the traffic to the internet or another location wherever it's pointed. That's called a default route. So in the Google Cloud, you'll use both, and you'll be getting in your VPC virtual routing. And that virtual routing is just going to be just like any other router in the world. The only difference is it's going to be software-based, and it'll be in your VPC. Now, you can create custom routes, which is that tells you, manually defines where you want your traffic to be sent. And you would always be doing this in networking. So nothing new here. So we also have firewall rules, and we have firewalls from the Google Cloud. The point is, firewalls are security appliances, and they're there to protect the perimeter of your network. And we're going to have multiple firewall options with regards to the Google Cloud. We have firewall components that protect our networks. We can potentially protect certain protocols, port numbers, source and destination. So it's going to be like any other firewall. So let's whiteboard it out. Generally speaking, you've got a firewall like this that connects to the internet. We'll call it a firewall, but it can also be between subnets. It can be anything that you want. But the point here is, and we're going to use lots and lots of these firewalls. Let's say it's for the internet. And the point of using the firewall is this. The firewall will not let traffic enter our protected environment behind the firewall. So we configure a policy on the firewall. And what I mean by the policy on the firewall is it allows our internal traffic to go out to the internet and return back. And the firewall is watching our traffic, so it knows to allow it back. It's called stateful. And that's great. But if an internet user tries to connect in, they won't be allowed. So we typically create what's called firewall rules. Now, you may hear the concept called the demilitarized zone and security, which obviously we're going to have all over the place. And what the demilitarized zone would be is, let's say we had a specific subnet off of the firewall. Everything internal to us is private IP addresses. So let's say our organization is using the 10.0.0.0/8 address space internally. This is a public subnet, so I'm just going to call it public IP address, so I don't use anybody's real address. Public subnet. And on here, let's say we have the load balancer of the public website, load balancer public IP address. And what we'll typically do is we'll create the firewall rule that will say, allow traffic of any of us, of whatever source addresses, potentially limited to a certain environment, through the firewall that are reaching this web server, or what looks like a web server, the front end of the load balancer's IP address. Any TCP traffic destined at port 443. That's web traffic. So realistically speaking, this firewall would only allow web traffic to this server or group of servers that's sitting in the internet. Those servers will obviously be hardened and protected because they're sitting on the internet, and yet no internal traffic can come inside of our environment. And that's why we create this demilitarized zone, to put things that have to be in the internet on the internet, and not allow openings through the firewall for the to allow in our internal environment to be seen past the internet. So that's why we're using firewalls. We can be using firewalls to protect us between other companies we do business with. We could use a firewall between VPCs if we want to connect our VPCs, but we're going to be using a lot of firewalls. So we want to enhance our security. We want to micro-segment our environment, and we don't want systems talking to each other that shouldn't be, because it increases risk. We can apply firewalls to routes to roots. We can do it to specific virtual machines. There's lots of firewall type options we'll actually have that we can work with. We also need to think about networking. So we need to intelligently plan our IP address subnets. We want to use the right size subnet. For example, if we had a subnet that could support 65,000 users, but we could never put more than 500 systems on a subnet because of broadcast traffic, then that would be a big waste of IP addresses. So we need to design our subnets right and provision and use the right size subnets. And don't waste IP addresses, and don't put our IP addresses in the wrong places. We need to plan this carefully. You're going to need a network architect's help for this. So remember, firewalls are going to act as critical security controls, ensuring only authorized traffic or allowed traffic can enter or leave a network. So we can do this. When it comes to security, trust nobody. Just assume everything is dangerous and you're inherently insecure, and you're going to have to design a lot of firewall rules, a lot of security principles to meet these needs. Now, there are this concept of network tags. These are likely to be tested on the exam. So the kind of tags that we're actually putting on these things. So network tags is the ability to apply firewall rules to a root or something like that. So be able to think about being able to apply these tags or firewall rules. So we might use a tag to target or exempt a certain virtual machine from a specific firewall rule. So the tags give us some control in our firewalls to be able to label certain things to exempt maybe only this subnet can talk to the internet, this server on this subnet can talk to the internet, and all the others can't.
So I kind of hope that it helps make sense.
So now we're going to be getting into the fun time real quick. Leo's got labs which she can talk about, but I just wanted to see if there were any questions. So, Leo, you want to talk about the next 2 labs that are coming up while we see if any questions come in?
Sure, Mike. We will basically demonstrate how to create that virtual private clouds. What is the underlying infrastructure needed to create the services in the cloud? And then we will create some virtual machines to show how things work inside the VPC.
All right, well, that sounds fun to me. So we'll get to that in a minute. Just a reminder that if for some reason you just joined us today, right now, we have the first 2 days available on our YouTube channel. You can go back and see it. We have a completely free guide that goes along with this. It's about a 550-page guide to help you pass the Google Professional Cloud Architect exam. It's a study guide for the Google Professional Cloud Architect exam that my team made. So make sure you sign up for it. Team just dropped it in the chat box. And also then on tomorrow, we're going to have a fun how to become an architect webinar. We'll go over the architect role, what we do. We'll talk about why it's safe from AI and one of the best roles moving forward. We'll talk about how to bypass HR, and I'll answer any question you want. So sign up. My team dropped the link for that in the chat box. It's all free. Get to meet you on Zoom, and I love meeting new people. Leo, are you ready for the labs? Anything to address, talk about before we go?
No, we are ready.
All right, well, let's get a little geeky and see Leo build this. I always love getting to see these demos. I'm an architect. See, we don't touch the tech in our lives. We're all about design, so it's fun every once in a while to see someone that's really capable with a lot of engineering background like Leo has 20 years build it. So let's get to Leo's labs.
Hello. In this lab, I will demonstrate how to create a virtual private cloud or VPC. I'll start here from the page cloud.google.com, and I will click the Docs option here on the top to open Google documentation. From the left side menu, I will click Networking, and then I will click Overview of Networking. The networking overview document or page opens here. And under the Explore Networking in Google Cloud, there is one document for the Virtual Private Cloud Overview. I will click the link to open the document. Here is the Virtual Private Cloud Overview document. There is a diagram here showing some regions and availability zones. And here there is one link for more information. See VPC networks. I will click this link to open the VPC networks document. This document explains what a virtual private cloud is and why this is needed when creating your IT systems in the cloud. And it also highlights what a VPC network does. It provides connectivity for your compute engine virtual machine instances. It offers native internal pass-through network load balancers and proxy systems for internal application load balancers. It connects to on-premises networks by using cloud virtual private network tunnels and virtual LAN attachments for cloud interconnect. It also distributes traffic from Google Cloud external load balancers to backends. Projects can contain multiple VPC networks. Unless you create an organizational policy that prohibits it, new projects start with a default network, and this default network has one subnetwork in each region. I will scroll down this document. Read the document to understand more about the virtual private cloud. And here we have a diagram that shows the VPC network in blue, some regions in green, and some availability zones on yellow. The subnets are in pink, representing the subnetworks inside each region. This labs works best if you have clear the concepts of regions and availability zones in the Google Cloud. If you need a refresher, please refer to the bootcamp content or to the Google documentation. You can use the search bar here, but I will right-click here to duplicate this page. And then use the search functionality to find regions and zones. The first link is the document about regions and zones. I will close this tab and go back to the diagram. And right now we will create this basic or minimum infrastructure for the virtual private cloud network. I will scroll down to the What's Next session. And I will open the Create, Modify, and Delete VPC networks and subnets in a new tab. I will right-click and open in a new tab, and I will switch to that document. I will scroll down a little bit, and here there is some important information about creating an auto-mode VPC network. And the important information reads, production networks should be planned in advance, and custom mode VPC networks are better suited for most production use cases. The first infrastructure we are going to build is an auto mode VPC network. This is just to compare the auto mode with a custom mode, which is recommended for production use cases. The first step on creating this virtual private cloud is to go to the VPC networks page. I will switch to the console, and from the top left menu, I will select VPC network and then VPC networks. Here is the default network, and as the documentation informed, it creates one subnetwork for each region. There are 41 subnetworks in the default VPC for this project. I will click Create VPC Network to start the process of creating the VPC network. I will name this Auto Mode VPC. And I will not explain all the aspects or options for creating this VPC network. Please read the documentation to understand the different options on creating VPCs. Here, the subnet creation mode, I will change to automatic, and this means this auto mode VPC will create subnets for me. I will not have control over any aspects of the subnets that are going to be created. Here I can select some firewall rules, for instance, to allow ping to test the connectivity and to allow SSH for communicating with the virtual machine. There are some firewall rules that are created by default. A deny all rule for ingress traffic. This means any requests that are coming from outside your virtual private cloud will be denied. And a allow all for egress, or any request that is created or originated inside your VPC, those requests are allowed by default. So all requests going out from your system are allowed. all requests coming into your system are denied. Here there are more options for dynamic routing modes, best path selection modes. I will leave them as they are and I will click Create. Now, the auto mode VPC is created. I can click its name to show some details about this VPC created using the auto mode. For instance, the subnets were created and some firewall rules were selected. I can click here to open the firewall rules that were selected. And this is it for an auto mode VPC creation. I will go back to the VPC networks page because now I will show the difference when creating a VPC using the custom mode. I will click Create VPC Network button and enter Custom Mode VPC as the name for that VPC. And here under the subnet creation mode, I will leave as custom because now I will customize the subnets. And here is the subnets part of the configuration. I will enter a name for a new subnet. I will call the first one subnet 1 and I will choose the region US West 1 for this subnet. I will leave it as a single stack IPv4, and for the IPv4 range I will enter the IP address 10.240.0.0/24. I will accept the other options here and click Done. This is done for one subnet. I will also create another subnet. So I will click Add Subnet to create this subnet 2. And this subnet will exist in the region US East 1. The IPv4 range for this subnet number 2 will be 192.168.1.0/24. I will accept the other options and click Done. I will select the ICMP and SSH protocols to be allowed by the firewall on this virtual private cloud. I will scroll down, accept the other configurations or settings, and then click Create to create this custom mode VPC. Now the custom mode VPC is ready. I will click its name to open the details. And as a comparison, this custom mode VPC has only 2 subnets, and the subnets, they have one specific range of IP addresses because I entered that information when creating the subnet. So the custom mode allows for more control over the infrastructure or the network and the subnetworks you are creating. I created this custom mode VPC with 2 subnets. This is not rare that organizations need to create more subnetworks or more VPCs. In this case, let's say there is a need to create a new subnet. How can we create new subnets once the VPC is already created? We can click the Add Subnet button over here. and then we enter the name of the subnet. I will call this subnet 3. The region will be US East 1. And there are some different options now, but I will leave as none as the purpose of this subnet. It's not use specific at this point. I will enter the IP range for this subnet, that is 10.2.0.0/16. I will accept the other options and then click the Add button to add this new subnet to the existing custom mode VPC. So this is a basic configuration for a custom mode VPC. If we go back to the VPC networks page, we see that there is a default VPC that was created when this project was created. There is an auto mode VPC that I just created some minutes ago. And there is the custom mode VPC, which allows for more control when creating the subnetworks inside the VPC. The information I used to create this custom mode VPC with its subnets is basically the diagram we have in this document. I use the regions and the names of the subnets with their IP address ranges to create the VPC as it is shown on this diagram. In a future lab, I will create the virtual machines inside the different availability zones following this diagram. In this lab, I demonstrated how to create virtual private clouds. I created one using the auto mode, and I created a second one using the custom mode, which allows for more control when creating the subnetworks inside the VPC. As I will use this custom mode VPC in the next lab, I will demonstrate how you can delete a VPC by deleting the auto mode VPC. To delete a VPC, you need to delete all the resources inside their subnets. This means network peering connections, cloud VPN gateways, cloud routers, serverless VPC access connector, and their connected services, firewall rules, and custom static routes. As I just created the auto mode VPC, I don't need to delete those resources before I can delete the VPC. To delete a VPC, you click its name, and then you have the button to delete the VPC network. Click that button, and I need to type in or copy the name of the VPC to this field, and then press the delete button to confirm I want to delete that VPC. In the next lab, I will finish creating this VPC, creating the virtual machine, and allocating them on the subnets and availability zones. If you are going to do that lab, don't delete the custom mode VPC yet. Leave the custom mode VPC because it will be used in the next lab. If you don't plan on doing the next lab, you can delete the custom mode VPC now, following the instructions that I will demonstrate now. I will now demonstrate how you can delete a subnet and how you can delete a complete VPC. Let's first try to delete a subnet without deleting the virtual machine. I click the subnet name, and I can click the delete icon here on the right to delete that subnet. Reminding that there is an existing virtual machine in that subnet. Or better, there are two virtual machines in subnet number 3, and here is the error. Let's go to the virtual machines page, and for the subnet 3, we will delete the VM3 and the VM4. Now the virtual machines are deleted. Let's try to delete the subnet number 3. Now the subnet 3 doesn't exist anymore. This is how you can delete a subnet you have no use for it anymore. I will go back to the VM instances page, and since I will demonstrate how to delete a complete VPC, I need to delete these virtual machines. And if there were any other services being used inside the subnets on this VPC, I would have to remove all the services as well. See the documentation to verify the specific services that must be deleted before you can delete the VPC. Now that the virtual machines are deleted, I will delete the VPC. To delete the VPC, you click its name, and then you click Delete VPC Network. You need to type in or paste the name of the VPC on this field, and then click Delete to confirm you want to delete the VPC. Now the custom mode VPC is deleted. In this lab, I demonstrated how to create virtual private clouds networks. I created one using the alpha mode, and I created a second one using the custom mode that allows for more control on creating the subnetworks. I demonstrated the whole cleanup, how to delete a subnet, and how to delete a complete virtual private cloud network. Thank you for watching.
Okay, welcome back, everyone. So we're here to see if anybody had any questions of Leo as it pertains to this lab. And if not, Leo, what's the next lab on?
Well, the next lab will be where I demonstrate how to create the virtual machines. I copied the end of the next lab to this lab because I wasn't sure they would be presented back to back. But
Okay.
now we will present the lab showing how to create the virtual machines inside that custom mode VPC.
Okay, good. So you're gonna take the virtual private data center that you created, and now you're gonna put some stuff in it?
That's correct.
Fantastic. Love it, Leo. Everybody give me a hashtag, Google Professional Cloud Architect. Maybe if you're here, give the video a like. Maybe subscribe to the channel if you're not a subscriber. And Chris, I guess it's time for the next lab. Oh, also, I want to remind everyone that if you just joined us, we've got a completely free guide that basically goes along with this Google Professional Cloud Architect training. My team put about 550 pages of content into that Google Professional Cloud Architect study guide. So please sign up for it. It'll be emailed to you. Tomorrow at 11 a.m., we're going to have some fun, and we're going to talk about how to become a cloud architect. We run one every week, but tomorrow we're going to do it at 11 a.m. We'll talk about what we do as architects. We'll talk about the skills you need as architects. We'll talk about how to bypass HR, which you definitely want to do if you don't have the perfect resume. And we'll talk about anything you want related to becoming an architect of any kind: cloud architect, security architect, AI architect, enterprise architect. And it's all fun and live and free on Zoom. So sign up. It's in the description and the chat box. And guess what? I'll meet so many of you tomorrow. And we'll be finishing after the next lab But we've got a lot more tomorrow. We've got a lot more Friday, and we've got plenty to go for next week. So I always like getting geeky. This is always fun for me. So, Chris, let's roll with the next one.
Hello. In this lab, I will demonstrate how to create virtual machines and allocate them in specific availability zones and subnets. In the previous lab, I created the infrastructure of the virtual private cloud, and now I will use that infrastructure to create the virtual machines and complete that suggested virtual private cloud from the document VPC networks. I will scroll down to that diagram, and in the previous lab, we created the VPC network. We created 3 different subnets in 2 regions, US West and US East regions. In this lab, I will create the virtual machines inside the different subnets and specific availability zones. Let's switch to the console. And here we have the custom mode VPC, and I will show the details with 3 different subnets that were created using the custom mode to have control over different settings. For instance, the IP address ranges for each one of those subnets. I will now open the Compute Engine VM instances page in a new tab. Switch to that tab. And then I will start creating the virtual machines. I will click the Create Instance button, and I will call the first one VM1. And this VM1 will be allocated inside the subnet 1. So the VM1 will be inside the subnet 1 and inside the US West 1A availability zone. If you need a refresh on regions and zones concept, please refer to the bootcamp content or to the documentation. But in simple terms, the region is a geographical area that contains a number of availability zones, and each availability zone is one physical data center inside that region. This means we cannot create new availability zones. They exist physically inside the geographic region. What we can do is to create subnets that span across availability zones. Let's create the first virtual machine inside the subnet 1. So this is US West 1 region. And I will select the availability zone US West 1A as in the diagram. For the disk of that virtual machine, I will select the custom disk, the custom image I created for the custom web server. I click select. And from the networking part, I will change the network interface because the default setting is to use a network interface in the default network. I don't want to use the default network, so I will click the delete button here on the right and click add a network interface. The network will be my custom mode VPC, and the subnet will be the subnet 1 that I created inside that region. Here is the subnet 1. So after selecting the region and the availability zone, I select in which subnet I want to allocate the network card of this virtual machine. I will accept the other settings and click Done. And then I will click Create to create this virtual machine. While this virtual machine is being created, I will create the second virtual machine. I will change the name to VM2, and the VM2 will be created in the region US East 1 in subnet 2 and availability zone US East 1B. US East 1 and zone US 1B. As I did in the first virtual machine, I will change the disk for a custom image. That is the custom Apache web server. And for the networking, I will delete the default network interface suggested. Click Add Network Interface. Select the network, the custom mode VPC, and the subnet is the subnet 2 inside that VPC. I will click Done and then click Create, and I will create the third virtual machine, call it VM3, and the VM3 will be this virtual machine inside the US East 1 region, US East 1C availability zone. I will change the boot disk to the custom image of the web server. Under networking, delete the network interface, click Add Network Interface, select the custom mode VPC network, and now I will select the subnet 3 to create this virtual machine. I will click Done and then click Create. So now we have one virtual machine in the region US West 1 in the subnet 1. We have one virtual machine in the region US East 1 subnet 2. And the third virtual machine is being created inside the region US East 1 subnet 3 zone US East 1C. So right now, each of these virtual machines exists in a different availability zone. Physically, they are in different data centers. I will copy the external IP address of VM1, open a new tab, paste the address here and press Enter to test if I can reach the web server. And it doesn't go. I will copy the external IP address of VM2, do the same. And when the VM3 is ready, I will copy its external IP address, create a new tab, and test if any of those virtual machines can reach the web server. So far, none of them can reach the web server. Let's go to the custom mode VPC page and then click the firewalls option. I click the arrow to show the firewall rules, and I can see we have one rule to allow ICMP traffic and another rule to allow SSH traffic, but there is no rule to allow HTTP traffic. We can click the add firewall rule here. Then name the rule as HTTP traffic, and it doesn't accept spaces. I will add a hyphen here, and it doesn't allow uppercase letters as well. I will change to HTTP in lowercase. The network for this rule is the custom mode VPC rule, and I will accept most of the defaults. One of them is the direction of traffic is ingress, meaning the HTTP requests are coming from the internet with destination of the web servers running in virtual machines in our network. The action for this rule is to allow any HTTP ingress traffic, and the targets for this rule, I can select different options here. There is one option to all instances in the network, meaning any virtual machine can be reached by those HTTP requests. There is one option to specify target tags, and another one for specified service account. I will select all instances in the network, and the source filter will be IPv4 ranges, and the range I will add here is 0.0.0.0/0. This IPv4 range means every address, every IPv4 address that exists on the internet is allowed, should be allowed by this rule. And I will, from the protocols and ports, I will leave specified protocols and ports selected. I will check the TCP option here and enter the port 80 for HTTP traffic. Please remember, for production, please use HTTPS, which is port 443. I will click Create to create this firewall rule, and then I will hit refresh on the virtual machines to see that they can connect to the web server now that there is a firewall rule allowing HTTP traffic into the network. So far, we have created one web server in this region and zone and subnet, one web server in this region, zone, and subnet, and one web server in this region, zone, and subnet. To demonstrate that subnets can span across availability zones, this virtual machine is inside subnet 3, but it exists in the availability zone US East 1B. When this virtual machine is created, there will exist 2 virtual machines in subnet 3, but each of these virtual machines exists physically in a different data center. One in the availability zone US East 1B, another one in the US East 1C. Let's create the VM number 4. The VM4 exists in region US East 1, availability zone US East 1B. Let's do the following. Let's leave the region as it is and see what happens. I will change the boot disk as I did for the other virtual machines, choosing the custom Apache Web Server disk or image. And now when I delete the network interface and try to add a network interface inside region US East 1, what will happen? Custom mode VPC, subnetwork, no subnetworks in this region. This means that in the machine configuration, I am trying to create a virtual machine in the region US Central 1 in any of the availability zones existing in that region. But when I try to create a network interface, I am trying to select from the existing subnetworks from the custom mode VPC, and I haven't created any subnet on that specific region. So I will change now the region to US East 1 and the availability zone US East 1C. So this is the location the virtual machine will physically exist. Now I can create a network interface connecting this virtual machine with the subnet number 3. I will accept the other parameters and click Done, and then click Create. Now the virtual machine 4 is ready. I will copy its external IP address and test if I can reach the web server in that virtual machine. And here is the hello world. If I go back to the VPC firewall rules and check the HTTP traffic, I will click Edit this rule, and I will change the targets for the allow HTTP traffic from all instances in the network to specified target tags. And I will enter the target tags web server, and I will click Save. Now I will go to the VM instance 4. And I will click Edit. And I will enter a network tag as web server for this virtual machine and click Save. So I changed the firewall rule. Instead of allowing the protocol to all internal virtual machines, I changed it to allow for specific target tags. Will allow the HTTP protocol to enter only the virtual machines that have the web server tag. As I created the web server tag in the VM number 4, only the VM number 4 should keep working after changing the firewall rule. The other 3 virtual machines are trying to reach, or the requests for those virtual machines are trying to reach the virtual machines, but no responses is being received. But the requests sent to VM4, they are replied almost instantaneously. So now if I go to the different virtual machines and add tags to them, enter the web server tag for the VM1, then for the VM2, and then for the VM number 3. Well, before I change the VM number 3, I will refresh. VM number 1 is already accessing the web server, VM number 2 as well. But VM number 3 is still trying to access without success. After I enter the network tag here and click Save, that will change for VM number 3 as well. There it goes. In this lab, I demonstrated how to create virtual machines in different regions, availability zones, and subnets. And I demonstrated that subnets can span across availability zones by creating one virtual machine in one availability zone and another virtual machine in a different availability zone, but the two virtual machines belong to the same subnet. I will now demonstrate how you can delete a subnet and how you can delete a complete VPC. I will go back to the VPC networks. Then I will click the name of the VPC, custom mode VPC. And here under subnets, let's first try to delete a subnet without deleting the virtual machine. I click the subnet name and I can click the delete icon here on the right to delete that subnet, reminding that there is an existing virtual machine in that subnet. Or better, there are two virtual machines in subnet number 3, and here is the error. Let's close this error. Let's go to the virtual machines page. And for the subnet 3, we will delete the VM3 and the VM4. Now the virtual machines are deleted. Let's try to delete the subnet number 3. Now the subnet 3 doesn't exist anymore. This is how you can delete a subnet you have no use for it anymore. I will go back to the VM instances page, and since I will demonstrate how to delete a complete VPC, I need to delete these virtual machines. And if there were any other services being used inside the subnets on this VPC, I would have to remove all the services as well. See the documentation to verify the specific services that must be deleted before you can delete the VPC. Now that the virtual machines are deleted, I will delete the VPC. To delete the VPC, you click its name, and then you click Delete VPC Network. You need to type in or paste the name of the VPC on this field, and then click Delete to confirm you want to delete the VPC. Now the custom mode VPC is deleted. In this lab, I demonstrated how to create virtual machines in different regions, availability zones, and subnets. And I also demonstrated that subnets can span across availability zones. I demonstrated the whole cleanup, how to delete a subnet, and how to delete a complete virtual private cloud network. Thank you for watching, and see you in the next lab.
Welcome back. So I hope you guys had fun watching Leo do some networking, setting up the VPC, putting some things in the VPC. I know I did. So we're at the end of today, but don't worry. We still have Thursday, Friday this week, and we also have all of next week. Leo, you want to share about some of the next labs you have are going to be about?
Sure. In this lab, I used a custom image. If you got curious about how to create a custom image, we have a lab exactly showing how you can create a boot disk for a virtual machine containing exactly the applications you need on that virtual machine and more. We will use the custom image to create virtual machines, to create instances, templates, so we can create auto-scaling groups with a different number of virtual machines.
Oh, that's fun. And if any of you remember what it used to be for me in the old days to image all these virtual machines and how much manual intervention it took, this is nothing like this. It's really cool. So I hope you all had a great time. I really enjoyed spending time with you. I see we have people from all over the world, and that just makes me happy. So welcome to everyone, wherever you're at. If you had a good time, maybe give this a like. Tell a friend, because we really want to do what we can to help as many people as we can. And that's why we do these free boot camps. You know, we've got them for almost any program you can think of, but today's is about the Google Professional Cloud Architect. So I'm not used to getting out a little early. We finished a few minutes early. I know we held you a little late on Mondays. So welcome. Enjoy the night. Have some fun. Be proud of yourselves. You guys have put up with a lot of deep content now. And it's not always the easiest thing to learn new things. So, you know, be proud of yourselves. You're working hard, and this is great. So I'll see you all tomorrow. Give me a hashtag Google Professional Cloud Architect. And I hope to see so many of you in the webinar on how to become an architect, which will be at 11 a.m. It'll be on Zoom. We'll go over how to become an architect. We'll talk about what we do. We'll talk about the exact skills you need and what you could do to get hired. And it's all free. That'll be in the description of this video if you're watching after the fact, as well as the chat box. Take care, everyone, and I look forward to seeing you tomorrow.